We spent a lot of time in Chapter 7 talking about gases. We're going to not spend nearly as much time, but I feel like we ought to give a little bit of time to liquids and solids as well. So in this section, we're going to talk about liquids. And some of these terms you've probably heard, some are maybe new. So when we talk about liquids, evaporation is where we convert liquids into gas. And this happens on your skin. It happens if you leave a cup of water out. And this is considered to be an endothermic reaction. What that means is it absorbs heat from the surroundings in order for this process to occur. Condensation is the conversion of gases into liquids. And so you may have seen this on the inside of a pot. If you've got a pot covered on the stove and you lift it up, there's usually some water underneath there. And this isn't, that's the condensation, because the top of the pot is cooler than the surface of the water where it's boiling, and so it's converting back into the liquid phase on that top. This is considered to be an exothermic process because it's going to be giving off heat. Vapor pressure is associated with the gas phase and the liquid phase of a liquid. The vapor pressure is the pressure exerted by gas molecules that are in equilibrium with a liquid phase. That is, when you've got a liquid phase, depending on what temperature you're at, you're going to have some gas molecules evaporating, and you may also have some condensing back. And again, it just depends on what the temperature is. In evaporation, though, we know that they're leaving. Okay, and so the vapor pressure of a gas is going to increase as you increase the temperature. So if I increase the temperature, the vapor pressure is going to also increase. The boiling point of a liquid is the temperature where the vapor pressure is equal to atmospheric pressure. And if you remember, one atmosphere is the same as 760 millimeters of mercury. So the boiling point, a liquid boils when its vapor pressure is the same as whatever environment it's in. If it's out in the open, then that's atmospheric pressure. So the stronger the intermolecular forces, the lower the vapor pressure at a particular temperature. So if you have stronger, like when you got, and we're going to go back to our old faithful examples of water and methane. Methane has stronger intermolecular forces because it has hydrogen bonds. And so since it's hanging on a little tighter, then fewer of these molecules are going to be able to leave. And so, and again, we're assuming we got both of these liquids at the same temperature right now. So fewer gas molecules, or fewer molecules in the gas phase, means a lower vapor pressure. With the methane, since it has weaker forces holding its liquid together, then it's going to be easier for it to evaporate, and so those are going to be escaping into the gas phase. The more gas molecules that are being produced, the higher the vapor pressure is going to be. So if you've got strong bonds, like hydrogen bonds, then you're going to have a lower vapor pressure than something that has only the dispersion or London forces. Another cool thing about liquids is viscosity. And the definition of viscosity is resistance to flow, but I like this one better. It's how thick is it, okay? And that's how you think of it. Okay, so honey, or if you're from Tennessee like me, sorghum, molasses, has a high viscosity. Water has a low viscosity. And if you've used much honey, you know, sometimes, especially when it gets thick, it's been sitting around for a while, it's very slow to come out of that little bear that you squeeze, right? And so if that is a high viscosity because it resists free flow. Water, though, you can squirt it right out, right? And so that's got a low viscosity. It's not really resisting flow. And this is, again, a property of these intermolecular forces that are holding this liquid together. Compounds with the strong intermolecular forces are going to be more viscous, and so that was true in our relationship we said with water and with honey, because honey is going to be more of those dispersion forces. Substances composed of large molecules are more viscous as well, okay? So our honey is more viscous, and the molecules that are associated with honey are much larger than water. Another cool thing about liquids is surface tension. Surface tension is defined as a measure of the resistance of a liquid to spread. If you put a couple of drops of water on a table, what you'll see is that it'll stay together and it'll have like a little dome shape. And that little dome shape is due to the surface tension. And basically what happens is when you're inside the water, so if we go down a little ways down in here in the water, all of these water molecules are going to have something else to be attracted to, right? But the water molecules that are at the surface aren't going to have anything to be attracted to that's above them. And so what happens is you get enough of these like this, and they almost form like some kind of little film. And if you're from the country like me, you ever seen a skeeter bug, we call them. I don't know what they call them in other states, but we call them a skeeter bug. They can literally stand on the water, and that's due to the surface tension, and it basically is enough to hold that little bug up. The stronger the intermolecular forces, the stronger the surface molecules are pulled down and into the liquid, and therefore the higher the surface tension. Stronger molecular forces, higher surface tension. Water has a very high surface tension because it has strong bonds, hydrogen bonding. When small objects float on the surface, they're really just being held up by the tension due to the surface tension on the surface.